Okay, this is a review of the SPC chart material for Clinical Process Improvement Program for the Partners Healthcare System. Huzzah, huzzah. So this lecture will serve as a review of the material from the last class, and I'm going to make a couple of videos, several, and subsequent videos will prepare you for the next lecture. So what was the purpose of statistical process control charts? Well, as the name implies, they're intended to give us some idea about the condition of some kind of process. Is it in control or not? And remember, we started with the run chart, and I'm not going to give you any of the history. I know that I'm the only one who's interested in the history of these things, so I'm going to spare you that. But remember, we started with the run chart, and the run chart simply arrayed data in a time series. So for our purposes of our discussion, we're going to use a variable, some variable data, which means that it was data that was measured. And generally speaking, we can know that something is measured because we used a tool, not a tool. We used a tool, T-O-O-L. We used a tool to measure it. Okay? So let's start with our old buddy operating room turn around time. And let's just say we measured 6 turnaround times. So we have a time series here. We have observations 1, 2, 3, 4, 5, and 6. Let's just say that over this time period we're measuring minutes. Let's say that the first one was 15, the next one was 25, the next one was 20, the next one was 25, the next one was 15, and the next one was 20. Alright, so it's all well and good to have these data, but what are we going to do with them? Well, the first thing we need to do in order to figure out how to, in order to plot out a run chart, is we need to know what the median is. Well, what's the median? Well, the definition of the median, it's a value around which 50% of the data are greater and 50% are less. Okay, so it's the midpoint of the data. Well, how can we do the median by hand? You can do the median using Excel very simply, but how are we going to do the median by hand? Well, we can put the data in a tabular format like this, and we can say we have 115, we have 125, we have 120, we have another 25, we have another 15, and we have another 20. So there are 6 variables, so we can count down 3, 1, 2, 3. The median is equal to 20. Alright, so that's pretty simple. Now we can make ourselves a run chart to array our data with the right data, right values. So we know that the median, we'll make the median red, that the median is 20. And what were our variables? What were our values? Well, we had 15, 25, 20, 25, 15, 20. So let's say that this is 15, and this is 25, and this is 20. So we had a 15, a 25, and we have, of course, time here This is observation 1, 2, 3, 4, 5, 6. So first observation was 15, second one was 25, third one was 20. The next one was 25. Observation number, well, it should be over here. Observation number 4 was 20. Observation number 5 was, I think, was 25. Observation the next observation was 20. The one after that was 15. Is that right? Can I have that right? Oh, I have it mixed up. So this one and this one need to change places. So then we went to 15, and then we went to 20. Okay, and to make a run chart, we very simply connect the dots. Nope, you get the point. Let's do that again. We connect the dots. And this gives us a run chart. Okay, well, this is a terrifically informative thing, except it doesn't really tell us if these variables are too high or these variables are too low. It doesn't really help us much at all. So the next step in the evolution of the statistical process control chart was actually the development of the statistical process control chart. You remember that was by Mr. Schuhart. And remember, we replace the mean with the median with the mean. Okay, so now we're going to talk about x bar. And it just so happens, which is equal to the mean, it just so happens that for these data, the mean of 15, 25, 20, 25, 15, and 20, if we sum those, if we want to calculate a mean, remember it's the sum, it's the sum of all the variables over the number of variables, which in this case is 120 over 6, which is equal to 20, so that's the mean. So we can replace our median with our mean. In this case, they happen to be the same number, since I have conveniently arranged it to be thus. So we need some notion, though, of how these data are going to be expected to vary. So recall that Mr. Schuhart's innovation was, or Dr. Schuhart's innovation was, to put these control limits on. And these control limits established a range of data that we would expect the process to normally vary within. How do we pick this? Well, for continuous data, well, for any data for that matter, we use this notion of the sigma. Okay, sigma. What is sigma? Well, sigma is the standard deviation. Standard deviation, or sigma. For those of you who have MPHs, you know that in a population we denote the sigma as actually small letter s. But we're going to talk about sigma as the standard deviation of our process. Well, what is a standard deviation? The standard deviation is a way of quantifying the variation within a pool of data. So that's a nice way to say, that's a nice way to be complicated and opaque, but it's really a number that expresses how variable a series is. If our 6 observations were 20, 20, 20, 20, 20, 20, and 20, we would have had a sigma of 0. There's no variation. So how do we judge what the variation is in the data that we had? Well, the definition of the standard deviation, to be absolutely compulsive about it, it's the square root of the variance. Okay? Now the variance, we're not going to get into, but we're going to embed the variance in our definition of standard deviation, so we get it here. Okay, so sigma is equal to the square root of the variance. And what is the variance? The variance is the sum. Don't be too freaked out by this big sigma. Now, those of you who have math phobia, all it means is the sum of, or the total of. Well, what we're going to total is the difference between each observation, which we denote as x sub I. Each each value that we observe and how that varies from the mean. And we're going to take that value and square it. And the reason we square it is simply sometimes x sub I will be bigger than the mean, and sometimes it'll be smaller. If we square it, then we don't have a problem with the signs giving us trouble. We don't have problems with one number being less than 0, another being greater than 0. And we divide this all by the number of observations minus 1. Okay, so for our data, let's just run a little table down the side here. Okay, so we know that the mean was 20. One, 2, 3, 4, 5, 6, and our observations were 15, 25, 20, 25, 15, 20. If we subtract 20 from 15, we have -5, and that value squared is going to be, turns out, -5 squared is 25. 5 squared is 25. That's 25 minus 20. 20 minus 20 is equal to 0. Squared is 0. 25 minus 20 is equal to 5. Squared is 25. 15 minus 20 is -5. Squared is 25. And 20 minus 20 is 0. Squared is 0. And then if we sum these, what do we get? We get 100. Okay, so let's go back to our formula. We can plug and chug. So we know that the sum of the squares of the differences of each of our observations from the mean is none other than 100. And we also know that there are 6 observations, so 6 minus 1 turns out every time you do the calculation is 5. So this is the square root of 20, which equals 4.47. We're going to shorten it to 4.5. Okay, so we're going to call sigma 4.5 for our process. Okay, simple enough. So now when we go back up here, we can pick one sigma is 4.5. Okay, so if we were to pick one sigma, ooh, boy, that's rough. Let's try that again. One sigma is 4.5 away. 4 out of our 6 variables are actually going to be outside one sigma. Now remember, our distribution density from the lecture, if these are normally distributed data, 1 sigma will be expected to contain 68% of the variables. But if we go to 2 sigma, we'll have 95%, almost 95.5% of the variables. Back to our control chart, we'll make this 2 sigma will be 4.5 times 2, which would be 9. Oops, sorry. 9, and actually it would be 29. And our lower 2 sigma, put a 2 in there, 2 sigma control limit would be 11. Okay, so now we have a process that varies between the 2 sigma control limits would be 29 and 11. There, we haven't used Excel, we haven't used anything other than our fingers and a little bit of math, and we've made a statistical process control chart with 2 sigma control limits. Okay, in our next lecture we're going to talk about how to pick control limits for non-variable data. I'll see you then.